So this is a four-layered if is a function, the activation function. So I will say it's a four-layered if activated neural network or multi-layer perceptron. Okay, so these are the steps for forward propagation. The layers are denoted in the superscript, the layer numbers. The input layer is actually the first layer, layer 1, and the hidden layers 2 and 3, and the final layer, which is the fourth layer, the fourth one. Now moving to the backpropagation procedure. The first strategy for backpropagation can be understood in this way. The computation of delta is equal to this, where this is the activation matrix, or say the matrix containing the activated units, and its difference, and the difference between this and the original target values y. Fine. So actually here the shape for del 4, shape of del 4 is 4 by 1. Now moving to del 3, which is this corresponds to the fourth layer. Now del 3 is W3 transpose del 4, as you know, element wise multiplication. Now I am writing a general term. Okay, this will be better for understanding, which is actually f dash of A3. Now here the strategy 1 holds. Like the strategy 1 actually comes into play, because this step is common for both. There are two strategies. For strategy 1, this step is common. This step can be understood in two different ways, hence the two strategies. Now this weight matrix, the original shape of this weight matrix is 4 by 5, which actually becomes 5 by 4 after transpose, and del 4 is 4 by 1, so it becomes after multiplication 5 by 1. And for this, if say you include the whole layer 3, all the 5 units, okay, so you will also get a 5 by 1 matrix. But in this 5 by 1 matrix, always the first entry will be 0, because this is a bias unit. Now these bias units, not only this, x0, a0 of 2 and a0 of 3. Now this will never change. Questions are this: these bias terms never change, they remain constant throughout, because these are constants by default, and differentiation of these constant is always equal to 0, and they are not connected. There is no connection to this unit, to this a0 of in the second layer, that is a02, from the first layer. Similarly, there is no connection of a03 from anything, from any unit in the second layer. So actually they remain constant, as there are no connections to it from its previous layer. So they remain constant throughout with whatever values you initialize, and it becomes actually equal to 0. And you will have different values. So this is actually a 5 by 1 matrix. Computing del 2. Del 2 will be equal to W2 transpose del 3 matrix multiplication with f dash A2. Now W2, what is the dimension of W2? W2 will be 4 by 5, which is actually here 5 by 4. And del 3 was originally the shape 5 by 1, but there is a 0 here. So we will neglect the first term and will include all the remaining 4 terms. So what shall it be? It will be 4 by 1. Okay. So this becomes 5 by 1, and again f dash 2 is actually 5 by 1 only, with again the first element 0. So again from this we can obtain a vector of 5 by 1 with the first element 0 and the remaining as it is. Like not as it is, you will get certain values. Okay, when you first here you will do the matrix multiplication, and then you will here you will do the matrix multiplication, and here you will do the element wise matrix multiplication, and then you can obtain uh, del 2, which is actually of the shape 5 by 1, but the first element is useless. It will be 0 only, as because of the bias present in it. So what you will obtain effectively a vector of 4. So you have obtained del 4, del 3, and del 2. You have the values of del 1, del 4, del 3, and del 2. Okay, now you will proceed for finding the gradients. Now you have with you del 4, del 3, and del 2. What you need to find is the gradients or the partial derivatives of j with respect to the weights. Say you have to calculate the partial derivative of j, that is the cost function, with respect to the weights from first layer to the second layer. Say this. So what will be its value? Its value will be actually del 2 a1 transpose. Now a1 is actually x. Okay, x transpose. So what is the original dimension of del 2? It's 5 by 1, but actually the first element is always equal to 0. So this actually becomes 4 by 1 effectively, because we will not take the first element, as it is useless because of the bias term. And what is the shape of x2? X it's 4 by 1, and x transpose is 1 by 4, so it's 4 by 4. Okay, and now what is the step which is remaining? C, this partial derivative of j with respect to w1, you need to calculate this for all the instances, for all the m instances. Okay, and the final step is the gradient descent step, which is w1 minus alpha by m del j del w1. Here the weight actually gets updated. Fine. This is the weight updation step. Fine. So in this way, W2 and W3 also get updated. Let me show you the updation of W2 and W3 as well. So now I will be showing the updation of W3 and W2. Okay. So now I will be showing the updation of W2 as for now. Del j del W2, that is the partial derivative of j with respect to W2, or the gradient of j with respect to W2, is actually del 3 times A2 whole transpose. Again, what is the effective dimension of del 3? It's 4 by 1, because the first element which makes it 5 by 1 is actually useless. So this is 4 by 1, and A2 is actually 5 by 1, including the bias unit. We need to actually also include the bias unit here. So it's actually 1 by 5 after transpose, so it becomes 1 by 5, and after multiplication this is 4 by 5. Okay, so now is the gradient descent step, which is w2 equal to w2 minus alpha by m. This needs to be calculated for all the m instances, m training instances, del j del w2. What is the dimension of w2? The dimension of w2 is 4 by 5, and it matches with this. You always need to match, like whether you are proceeding or whether your step, whether you have calculated any wrong, whether there is a calculation mistake or not. Always check with the shape that you have. Similarly, let's move on to W3. This will be 4 and this will be 3. What is the shape of del 4? Effective shape. As this has no bias unit present here, so it's 4 by 1 only, and this is 1 by 5 as usual. So This will be 4 by 5. Again, it complies with W3, which is actually 4 by 5 as well. So in this way, the weights are updated. And you need to calculate this for all the m instances and then again divide this by n. So this forms the first strategy of backpropagation. Now moving on to the backpropagation second strategy. The second strategy is quite similar to the first strategy, but there is a conceptual difference. Del 4, the formulation is the same as the first strategy. Now for del 3, the formulation is a bit different. Okay, the formulation varies from del 3. Here in del 3, we know that the bias units are constants. Their derivative will always be equal to 0. So this W3, the expression, keeping the expression same, certain minor changes are being done. Like this W3 doesn't include the bias term present in the third layer. So the dimension of W3 here becomes 4 by 4. And what is del 4? Del 4 dimension is 4 by 1 as usual. So this becomes 4 by 1. Also, f dash 3, as the derivative of the constant term is always equal to 0. So the bias term is left over and the remaining, the derivative of the remaining terms are calculated, okay, which makes it 4 by 1. So del 3 is originally of the shape 4 by 1 only. It will not be 5 by 1 in any case. Similarly, del 2 is also of the shape 4 by 1. Now when you will be calculating the gradient del j del w1, which is delta 2 a1, that is actually x transpose. Now delta 2 is here. What the shape is only 4 by 1. And what about a1? What about a1? The a1 is actually x, so x is 1 by 4, so this is 4 by 4. And you need 4 by 4 only for to match it with the shape of w, and again execute the process of gradient descent, that is w1 equal to w1 minus alpha by m del j del w1. Okay, so the second strategy is only just neglecting the derivative of the constant term. Now, in a sigmoid activated, if f is a sigmoid term, or say a sigmoid function, it may seem that as the bias terms are equal to 1, so their derivative, so their derivative is always equal to 1. It may seem, and it is true also. It complies with the formula, because actually in the calculation of del 3, the actual expression will be if f is actually a sigmoid function. So it will be A3 matrix multiplication 1 minus A3. Element wise matrix multiplication. Fine, this is element wise matrix multiplication. This is also element wise matrix multiplication. And for the first bias term, as the bias term is generally initialized to 1, it seems that it will be equal to 0. But actually, as it is a constant, it will always be equal to 0, irrespective of what constant is in what value is initialized to these bias terms. It will always be equal to 0, and hence the first term is always neglected or stripped away. This is another explanation, or just clearance of the concepts, because invariably what the value of the bias is, as it is a constant, their derivative is always equal to 0. Now there is a regularization term which is also sometimes introduced, which is, as we know, JW is the binary cross entropy function I is equal to 1 to m yi log of, actually this is a4 in our example, okay, plus 1 minus yi log of 1 minus a4. Fine. Plus for L2 regularization, this is the extent of regularization, lambda term, L equal to 1 to L minus 1, I equal to 1 to SL, which is the number of units, J equal to 1 to SL plus 1, that is the number of units in the successive layer, WJI. This is actually the matrix index, and it does not include the zero terms, because as we know, we don't regularize the uh, coefficient attached with the bias term. Okay, so this is what is the regularization term. Now, as this is the regularization term involved, so when you are calculating the gradient of J, this regularization term is actually included along with this, along with the gradient descent steps as well. So W, say of 1, or say L, is equal to WL minus alpha by M, the expression of del J del W0. Obviously this will happen, but along with this there will be an additional term J. Actually J is this J is excluding the regularization term. Okay, I'm separating out this is the J, say this is JR. Okay, so JR is actually J plus this is the regularization function, so I am terming it as R. So we need to include the partial derivative of this R here. So this is actually lambda by M times W L. Okay, and this W does not include zeroth indices, that is the zeroth row or the zeroth column, because those are not, those do not take part in the regularization procedure. Okay, so this is the whole explanation of the backpropagation along with regularization. And finally I just only want to write down the general step, that is the general formula for calculating the gradient or the partial derivative after you are done with all the del values that is left over. After you are done with all the del values, that is you have del 4, del 3 and del 2, the final expression, this is the gradient accumulator, which is actually initialized to 0, but it is uh, it is loaded for each and every instance, and it is actually equal to plus del L plus 1 matrix multiplication with AL transpose. This is the most important expression for backpropagation in multilayer perceptron. Thank you.